Here is a brief introduction to the course of Engineering Design. This Living Technology course allows students to learn the ability design thinking through integrated ideas. At the senior high school level, we focus on the study of engineering design methods to build the ability to integrate and apply practice and interdisciplinary knowledge to respond to technological developmental trends the future capability needs. Therefore, this engineering design course, with in-depth technology outline, thoroughly discusses the learning of engineering design processes and integrates basic compulsory design manufacturing capabilities with a complete course on practical experience in product development, testing and assessment, and prototype manufacturing. All of these important learning contents of the course. The learning content of the elective course further studies a compulsory course in depth, with emphasis on technology integration concepts that explore the building of practical capabilities, with emphasis on learning through project making, which allows students to experience engineering-oriented design and manufacturing, and provide them with reference for future studies and career options. So the goal of this engineering design course is for us to learn methods through engineering design, process steps, and with design project activities, learn and understand the interaction between technology, engineering, science, and mathematics. Make good use of technological knowledge, creative thinking, and problem-solving capabilities. Correct technological values and attitudes, and interest in technological research and development. Resource integration, project management, effective communication, and teamwork abilities. An ability for engineering design to conduct experiments, analysis, and data interpretation. These are all important learning objectives for this course. During the process of engineering design, critical thinking is an essential skill. Therefore, engineering education emphasizes design thinking and how to use critical thinking during the process. Interdisciplinary integration becomes very important. Therefore, this course is designed to utilize project activities as teaching method through the experience of practical engineering design procedures, improve students' abilities of implementing critical thinking in design and production. Here we have the layout diagram designed for our course. For the theme of our activity, we will use compressed air racing cars as our design objective, blending the exploration of science and analysis of mathematics, the design of art, technological skills, and engineering design knowledge across different scientific disciplines to guide students in the learning of solving problems of the real world. This includes what is known as conceptual knowledge, which allows students to thoroughly perform design thinking judgments, and the other being procedural knowledge, which is the knowledge required to analyze and solve problems during the design manufacturing process. This cross-disciplinary approach to learning can help students develop abilities to analyze, determine, and solve problems of the real world. For the actual activities, we have planned 4 exploration and experimental activities to guide students in their learning of design thinking.
Here we refer to Professors Fan Sichun and Yu Guangzhao's engineering design process.
In the problem definition, condition, restriction, and data collection stages with the focus on design manufacturing of
the chassis and the axle system.
We arrange an experiment about rolling resistance on an inclined plane, followed by a development plan and predictive analysis. We shall mainly use 3D modeling and digital analysis for learning. For the predictive analysis method, we shall use simulation software. For fluid experimental analysis, we shall perform simple diagnostics. Next, we will choose a plan to perform modeling testing. Here we will finish the production of a car chassis prototype and perform wind tunnel aerodynamic experiment. To further comprehend that for the actual production of the car, the actual results of the drag efficient and air efficiency. Next is the test evaluation and optimization. After performing modifications, optimization corrections, we perform compressed air propulsion testing. Here we can understand our car's overall design efficiency and how our car's performance is improved after optimization corrections. Hello everybody, I'm Datong Senior High School's Life Technology teacher. In Datong High School, I am very happy to be appointed instructor for filming project for the
Ministry of Education's online course.
For this course, we have combined specialized knowledge from operational skills from 2 previous life technology credits. For example, we use students' previously manufactured prototypes to further learn about the manufacturing process of certain materials. For example, students may not be familiar with metals. We will use metals for strengthening the structure. In terms of strength effect, it has better results. It belongs to an emerging branch of life technology application. For example, 3D printing model analysis, CNC engraving, and laser cutting will all be included in the learning activities within our practical course. Design thinking is the most important concept. For our interdisciplinary integration through the conceptual knowledge already learned by our students, we combine it with procedural knowledge from our life technology implementations, and we design a car that has good performance and that be propelled at high speeds with compressed air in a short time. This kind of car may be a racing type of car, so we can learn from references such as supercars or some racing cars, and learn related knowledge about dynamics and aerodynamics. In a low driving resistance setting, we design a car with good performance. We combine all into this activity as the overall theme for our learning. For a more advanced engineering predictive analysis, we will allow our students to learn about more advanced 3D modeling, and through this model, we will perform some digital engineering analysis to perform a simple evaluation and let students understand how these so-called scientific or technological advances can provide predictive analysis in our engineering design to achieve the creation of a model, followed by choosing a plan and then manufacture such an engineering design that blends all explored knowledge and can also make such designs become more efficient and fulfill our original design's expectations to create an ideal race car. Next, we will show an animation to give a simple explanation regarding the engineering design processes. Problem context. Ming and Mei took an elective course on in-depth life technology. The teacher wanted them to design a compressed air-propelled race car. He played videos about some creations and competitions for them to watch and explained the relevant rules for the creation's design. He wanted them to search for some reference materials for vehicle design first, and they would discuss and research together for the next class. Step 1. Define requirements or problems. Before starting design production and problem solving, first we need to understand what our requirements are. What is the goal we are trying to achieve, what the functions are, and the reason why our engineering design is carried out. This can help us analyze the key points of the problem and clear out blind spots. Ming and Mei thought about the engineering design process learned previously. First, they had to find out what the key to winning was in those compressed air racing competitions. I'll search online for some videos of past compressed air racing competitions. Let's see if I can find some inspiration. Okay, I'll consult with Teacher Jay, ask him for some pointers about the key steps of our racing car design. Step 2, study the requirements or problems. From the proposed requirements, define the confronted problems and restrictions, list all requirements and problems in order to review and think all possible solutions. Send a line message to Teacher J and arrange a meeting time. I'll search online for relevant information about vehicle design. Step 3. Develop a feasible solution. Sometimes a problem can be solved directly using our own knowledge and imagination. But most times, we need new knowledge and information to help us obtain the best solution. Therefore, further research is essential. Searching online, looking for information, consulting experts, etc., all are available steps. I found online about 3 different kinds of racing car production: handcraft, 3D printing, CNC engraving. First, we will draw design sketches, do 3D modeling, and then choose the material for our compressed air racing car. Step 4. Choose the best solution. Use all gathered information to develop feasible ideas and solutions. Here we can skip to step 6. We can test and evaluate solutions to predict and analyze the feasibility of each solution and choose the best solution. These designs look pretty good. Let's choose one to produce. Step 5. Create a prototype. According to the best solution chosen, we make further plans to produce a prototype model. The prototype model can be produced with lightweight material to help evaluate the feasibility of the solution. We will use 3 different materials to create our prototypes and see which one can pass the testings. Step 6. Test and evaluate solutions. According to relevant theories and restrictions, predict the feasibility of each solution. This step can help us choose the best solution and can be used in testing and evaluation after prototype creation. From the wind tunnel test results, we found out that our car's air resistance is too big. We need to correct that. Step 7. Communicate the solution. Communicate the test results. If corrections and improvements are needed, we go back to step 4. Search again, whether there are better solutions. Teacher J said that the body's height and contour line can affect air drag. Let's do more research. Step 8. Redesign. Review the solution's results. Think about what can be improved and try using conceptual knowledge to modify or redesign, blending in the concepts for optimization. Apart from lowering the body's height, we can also add a spoiler. The spoiler design can increase air drag, can improve the car's stability, and increase its speed and safety. Step 9. Finish the design. Finalize a solution for the engineering design problem and solve the initially proposed problems. This step is an indicator for the completion of a phase task, but does not mean the finishing of all relevant designs. In the future, other requirements for this problem may appear, and the process of engineering design thinking will be restarted. Okay, we're done. Next time we can try and equip our tires of different materials. If a problem is encountered again, go back to step 1. Perform engineering design thinking process again to solve the new problem. Here we will use the compressed air racing car project to explain the engineering design process, steps 1 to 8. Step 1. Define the problem. Defining the problem refers to all reoccurring conditions and restrictions and relevant problems that need to be cleared or solved, which need to be defined at the early stages of the design. For example, the compressed air racing car project that we are producing comes from a technological education activity started in American junior high schools trending in the 1950s. Students had to design a creation for the racing car theme. There are many different competition formats. The fastest ones use CO2 gas cylinders. Its driving force could make the racing cars achieve speeds up to 120 kilometers per hour. These are the dimensional restrictions for the racing car and power specs. We will give a brief explanation For this type of racing car, its length should be around 20 centimeters long. In other words, 200 millimeters long. It should be 80 millimeters wide and 50 millimeters tall. For its driving power, there are two specifications, one being a 6-gram gas cylinder and the other being a 12-gram gas cylinder. Step 2, study the requirements. Here, we will need to study the key design factors for the race car, including the maximum speed and momentum in the shortest possible time, reducing driving resistance, so speed will be our most important goal. According to this goal, we will study the design direction regarding the type of our target product. It's more likely to belong to the category of a supercar or racing car. Everyone can gather information towards this direction. All the product development procedures have a similar structure as this figure. Regarding the learning key points for engineering design product, we can divide into 3 phases according to the product development procedure. The first phase is design thinking. Here we need to understand vehicle design from this product. Regarding the analysis of its requirements, we need to find out the key design features of our product, plan organizationally for our design team to perform further studies. Next, we will advance towards the conceptual design of our product development, as well as its relevant design planning. Here, the engineer design learning is about 3D modeling and predictive analysis, these two important steps providing engineering design strategies and diagnostics. Next, our product will advance towards the next step of the design phase. The main focus of our learning will be put in prototype production and test evaluations. Prototype production refers to the manufacturing of our first sample of our product. In this phase, we may use appropriate materials and different kinds of manufacturing equipment to finish the prototype that meets the quality required for engineering analysis. Here, we may need to constantly modify the product so that it can be improved to a better degree, to a better level. This is also known as the optimization process. For the final development phase of the product, we need to think about how to mass produce and need for future marketing so that the product can be more aesthetically pleasing, as well as measures for operational management systems. These are the main points of attention for the study of requirements and the industrial design process. Step 3, developing a feasible solution. The development of feasible solution needs to gradual formation of a concrete shape. To facilitate further analysis and discussion, modeling is a system that allows the showing of the design's products, features, and functions, which can be further expressed through the form of images, physics, and mathematics. The method for engineering design mostly used today is the creation of a computer 3D model. When facing a design problem in the beginning, there is only a vague impression. This impression will gradually form in the mind after discussions and drawings. This is the important step for the development of a feasible solution. The in-depth modeling ability in high school level life technology requires the drawing and creation of 3D models. Not only be able to clearly convey ideas, but also combine with CAM computer-aided manufacturing or CAE computer-aided analysis tools. To finalize a higher quality industrial engineering product, step 4, choosing the best solution. The choosing of solution needs to be based on objective facts and make good use of scientific and research methods. To predictively analyze and evaluate. Predictive analysis is a type of systematic thinking, and its purpose is to explain in detail all problems that happen during the design process. Here we can predictively analyze the best design out of many solutions available and choose the best solution. When facing different solution choices, a logical way of thinking for decision making is taken based objective standards and an appropriate solution for the product design is chosen. In this phase, we finalize 2 to 3 different 3D modeling creations and use fluid mechanics and finite element analysis techniques to perform predictive analysis. Within the same analysis conditions, evaluate each model's efficiency, and choose the better design to advance towards the next phase for prototype production. Step 5. Create prototype. Creating a prototype is to simulate the complete experience of the product, so the material's structural strength and quality needs to be able to meet the conditions for subsequent test conditions. The movable parts and the axle mechanism also need to move flexibility. So apart from handcrafting, if digital machining could be used, it would be ideal. These creations shown below, we used handcrafting, 3D printing, and CNC engraving. To finalize a prototype that meets the design conditions, the in-depth prototype production ability for high school life technology requires the use of diverse materials and tools to produce a prototype that meets the requirements for engineering design analysis evaluation. To manufacture the works for this project, students using the tools to make this topic. Step 6. Test and evaluation. Test and evaluation is a scientific method used to review the pros and cons of a design solution. It requires objective and multi-oriented measurements to correctly review the product's efficiency. The engineering design process, with regards to analysis and evaluation of conditional restrictions, as well as choosing of feasible solutions, not only requires basic scientific knowledge, but it relies more on the performance of tests and evaluations. Here, we will mainly consider the compressed air racing car. The objective for testing and evaluation is towards speed. Testing the creation speed will serve as a final evaluation to determine whether it's good or bad. For other testing and evaluation methods, we shall use wind tunnel to test the prototype car's wind resistance. And after continuous improvements and optimizations, we will use compressed air propulsion to test the improvements of the prototype speed. Step 7, the redesign. Redesigning for optimization is to find the best solution from the combination of all the best criteria that meet the restriction requirements. Or it's the improvement of the original design due to the finding of new problems after testing and evaluations for our compressed air racing cars project. Whether it is the improvement of speed or driving stability, the process of optimization is to slowly and constantly making it better. Therefore, optimization does not mean redesigning and redoing the creation, but the adjustment and partial modification of the original design. This is the principle of design optimization. Constant improvement allows the design to reach better performance for our racing car's original design. Apart from increasing its speed, we also added a spoiler to improve its driving stability. Therefore, the overall driving efficiency further gets an improvement. Step 8, finish the design. The design ultimately needs to come to an end due to time and resource limitations. Students can organize all testing and research information, design sketches, photos, and engineering notes used during the course activity to produce a complete learning history database. The experience of a complete engineering design process can also provide reference for future design production as well as career planning. Here we can see that the students have completed many unique and refined creations. They took pictures of their creations and organized their engineering notes and photos to produce a history file to be proud of, which is a perfect ending for our engineering design project course. This was our first class for our engineering design project. We will arrange a hands-on activity every week. This week's topic is to finish the engineering design notes. The first project is about data collection. Please use the computers in the classroom to search for 3 world-famous and arduous racing competitions using illustrations to explain each racing competition's design features. Please refer to the learning content and the engineering design notes 1. Also, the teacher has placed some supercar models in the front of the classroom. Feel free to come up to the front and observe and enjoy. These supercars are real from experienced brands. They strive for exceptional performance on the track and are worthy of our observation and learning.